analyze on there. And this is kind of poses a security risk. And as we have seen in the recent years, data breaches are becoming increasingly more common. And actually, that one, why you shouldn't trust Facebook, that's especially relevant, I guess, given what's been happening in the past few days. So the attackers in these cloud-based data breaches vary in their abilities. So some are external attackers that try to kind of hack into the system, breaking into the network from the outside, right? So these are more external attackers. But attacks can also happen internally, right, within a company. For example, when a curious or careless employee misuses company data, or possibly when there is a government subpoena. So to fully protect our data, we would like to assume that the entire server side can be compromised. So we want to be able to protect against a strong attacker. So now the question is, how can we actually protect our data and computation while preserving the original complex functionalities of the analytics system? So you could do this using a purely cryptographic approach. For example, you can use something called fully homomorphic encryption that allows you to kind of compute directly on encrypted data, and you can think of it as basically fully functional. But it's still more of a theoretical construct, I guess. So if you actually implement that in practice, it's quite slow. You can have specialized solutions like CryptDB, ARC, and CBED, but what these systems do is that they give you much more practical performance, but then they're often restrictive in their functionalities. But there's an exciting alternative called hardware enclaves. That's kind of this recent development in trusted hardware that promises full functionality. So you can run kind of arbitrary code inside with very small loss in performance and with kind of a lot of security guarantees. So I think probably, SGX has been, or hardware enclaves, I guess, the concept of hardware enclaves has been kind of out there for a few years, so you probably have heard of it. But in case you haven't heard of it, I'll just give you a kind of quick overview of what they are. So these are hardware-enforced secure execution environments that allow you to run your code securely on top of an untrusted operating system, even in the so even if the if the operating system itself is malicious, you can still run your code securely inside the enclave environment. And what the enclaves provide is something called an encrypted memory region, EPC, such that you can actually keep your data, secret data inside, and I can access the secret data within the enclave environment, but from the outside, from the attacker's perspective, everything is encrypted. So what this gives you is the ability to protect against an attacker who even has root access to the system. Another cool thing that secure enclaves provide is something called remote attestation. So this allows you to kind of load your code securely in possibly a remote machine, in a remote enclave somewhere. So the way you do this is that you can kind of transfer your code from the client to the enclave, and then the enclave itself, right? It provides this hardware mechanism that allows you to do a measurement of the code and any of the state that you load into the enclave, and produce a hash after the measurement, and give the hash back to you. So if you check that the hash is indeed what you expect it to be, then you know that you have loaded all your state correctly and secured into the enclave, into an enclave environment. So these are kind of the important features that allow you to allow us to do secure computation in the cloud.
So what prevents information from leaking out of the enclave? And also, what reason do you have to trust the enclave? I guess is another question. If considering that your cloud provider is like, oh yeah, it works great, or Intel's like, oh yeah, we give you SGX, but guess what? SGX is flawed, or guess what? We've loaded some alternate microcode that compromises it in such a way that you have no way of knowing.
Yeah, that's kind of there are a lot of subtle, I guess, points to that question. So I mean, first off, the enclave itself, right, just from a technical perspective, I guess, it, again, like as I mentioned before, it has this memory region called EPC that you keep everything that basically is your runtime, everything is encrypted. So if an attacker tries to look into memory, for example, then it will see it's encrypted data. So so that's kind of more from the technical perspective, why SGX allows you to run things securely in the cloud. And as to the question of whether you can trust SGX at all, I mean,
I guess the question is, how do you know that there aren't side channels that can leak your information?
Well, actually, there are side channels, which is kind of the one of the things that we're trying to tackle in this paper. So absolutely,
the thing is trustworthy to begin with, which is questionable.
Yeah. So I agree, and actually, I mean, I think just kind of going back into the history of SGX, I think what they originally started with was they were trying to develop a system that's used for, I guess, DRM purposes, not really for cloud computing. But then they saw that, oh yeah, there's this great other use case for that. So actually, in the original paper, I think they just flat out said, this is not secure against side channels, and I guess I'll explain more into detail what the side channels, particularly in our paper, were trying to tackle. But I think, and I think with all the recent, I guess, Spectre and meltdown attacks, that's even more relevant. So yes, I think trusting SGX, I think SGX as a hardware, I mean, it is new hardware, so there are more improvements that can be made to it. I think from a research perspective, I'm rambling a bit early on in the presentation, but from a research perspective, I actually think that like one direction I would like to explore later on would be to kind of use SGX for kind of integrity purposes and not for privacy purposes. So you can kind of decouple those two so that, I mean, if the SGX is completely compromisable, then you're kind of, I guess, screwed in some sense. But then if you are worried about side channels, then maybe you could decouple in such a way that, within the enclave, you take care of the integrity part of things, and then outside the enclave, you use some more crypto techniques to make it privacy preserving. But yeah, I mean, we can, I kind of jumped too far ahead, but we can, talk more offline if you want about this issue. So, okay, but so far, questions about how kind of SGX works, or okay. So for that, we'll assume that SGX is trustworthy. Okay, so there have been some recent systems that use enclaves to provide security. So most notably, Haven from OSDI 2014 and Scone from, I think, OSDI 2016 and BC3. So Haven Scone, for example, they provide secure single machine computation, and BC3 supports a kind of like secure distributed MapReduce computation. So these systems are really nice because they, using SGX, they give you full functionality. They have great performance and strong security guarantees. And the negative is that they don't protect against more sophisticated side channel attacks. And in this paper, we're kind of trying to look into this specific side channel attack called data access pattern leakage. Okay, so access pattern leakage, I mean, what is access pattern? I mean, this is literally, I mean, what it sounds like, right? So you have we have two kinds of access patterns that we're concerned about. One is memory access patterns and one is network. The other one is network access patterns. So for memory access patterns, it's literally just, like which memory addresses. So the attacker can learn information by only observing which memory addresses you are accessing during your computation. And the network one is pretty similar. This one is, they can observe which machines you're accessing, which machines you're sending messages to, and how big the messages are. So that's what access pattern is. And here I'll give an example of specific attack, I guess, using network access pattern leakage. So let's imagine here we have a table of patient records, and let's assume that, so we have the patient ID, name, age, and disease, and let's assume that the each row is encrypted separately, right? And we want to run a simple aggregation query on this table. And usually, one way to do this is to, let's say you're running on a distributed analytics system. So one way to run this query is to execute a hash-based aggregation algorithm where each record is shuffled to a machine based on the disease type. And then, you can, let's say, you have a patient ID, name, age, and disease. And let's assume that, so we have the patient ID, name, age, and disease, and let's assume that the each row is encrypted separately, right? And we want to run a simple aggregation query on this table. And usually, one way to do this is to execute a hash-based aggregation algorithm where each record is shuffled to a machine based on the disease type. And then, you can, group run the aggregation query on the machines afterwards. So notice here that an observer can actually observe the amount of network traffic that's happening during the computation and see that 4 records were shuffled to the first machine and 2 records were shuffled to the second machine. So with some prior knowledge, public knowledge even, about the disease distribution, for example, by diabetes is twice as common as cancer, then the attacker can conclude that the first group is diabetes and the second group is cancer, right? So afterwards, the attacker, again, like this is a pretty powerful attacker who has root access to the systems, right? The attacker can backtrack records to see exactly which patient record corresponds to cancer. So in this case, it's row 3 and row 5. And now let's say a patient comes in for a checkup or treatment and his patient record is retrieved. Right, so that's a simple filter. And because the attacker already learned some information from the previous query about the disease of each encrypted record type, the attacker can now correlate the disease, in this case cancer, right, with this particular patient. So in this case, he learns that our patient has, this particular patient Alice has cancer. So this is a pretty powerful attack, and I'll just show you some kind of research prior work on how much leakage you can how much leakage there is from access patterns. So for example, the memory access pattern paper, leakage paper, was able to, so what they did was that they kind of loaded applications directly into SGX, and just based on the page fault page access patterns, I suppose, they were able to extract complete text documents and photo outlines based on that. And there's another paper that shows that, kind of similar to the type example that I showed before, that using network access pattern, you can extract age, gender, and address of individuals during a kind of database analysis query. So, this is some serious leakage here. So our goal is to build a system that allows you to do oblivious distributed analytics, where oblivious here means that access patterns are independent of the data content. So basically, the computation doesn't leak anything about access patterns. And this is our system called Opaque, which actually stands for something, Oblivious Platform for Analytic Queries. I didn't actually come up with a name, but so thanks to my lab mate. So what we did was that we implemented the system on top of Spark SQL, and we chose to implement Opaque at this relational algebra layer because it can support a wide range of analytics workloads, such as just plain SQL, machine learning, and graph analytics, and also introduce opportunities for query optimization. In Opaque, we assume the following threat model. So first, we assume kind of what the SGX assumes, I guess, which is a powerful attacker who can compromise the server software stack, including the operating system. So we're not assuming that you can compromise the trusted hardware. This is in our case SGX or the client side. So we assume that the client who's issuing the queries is trusted.
Even though compromising the software stack might allow you to load new firmware for the CPU or something, potentially, right? That's how they patch Spectre, right? Is you need to load microcode.
Yes. So we do assume that the entire, I guess, SGX, yes, including the microcode is also secure. Right. So in addition, actually, for Opaque, we from our system design perspective, we kind of assume that we have a small region of oblivious memory. And this is not currently implemented in the real SGX hardware, but there are a lot of more researchy prior work on how you could achieve this. So for example, TSGX allows you to kind of achieve a memory, a region that is not susceptible to page fault attacks. And there's other papers like Ghostwriter, etc. And you can do this via hardware mechanisms as well. But yeah, I can talk to you more about that later offline if necessary. Okay, so with that threat model, here are our security guarantees, more informal, I guess. So first of all, we provide data encryption and authentication. So this is kind of derived directly from SGX. Additionally, we have a protocol for providing computation integrity so that the client can actually check that the computation result was correct and was not affected by attacker. And the third one that we achieve is obliviousness. So in this case, we want to ensure that the memory and network accesses of a query, right, is the same for any two inputs with the same size. Yeah, I guess I won't go into that too much, but basically we can even provide, so I'll probably come back to this later. But yes, but basically obliviousness, the guarantee is we're trying to prevent access pattern leakage. Okay, so the challenge that we face in our paper is that obliviousness is fairly expensive. I mean, just intuitively thinking about it, right? To make sure that access patterns are not leaked, you kind of have to kind of make extra accesses, right, in order to hide the original real accesses. So that kind of intuitively, it will be expensive, right? And actually, prior works, I think it was Oblivious, showed that you can have up to 6 orders of magnitude of performance overhead. So it's definitely a challenging problem. And to deal with this problem, we came up with a 2-part solution. So the first one is we implemented new distributed oblivious SQL operators that rely on some interesting oblivious primitives, which I'll go into later. And we also introduced, from the more systems database side, we also introduced novel query planning techniques that allow you to further optimize these queries and improve performance. Okay, so questions so far?
For your embedded encryption, is it symmetrical or asymmetrical?
Oh, we do symmetric encryption. Yeah, okay. All right, so now let me jump into kind of the more technical details of how Opaque works. So Opaque has kind of different layers of components. So the first one is the data encryption authentication part of the system, which again, a lot of that is kind of provided by SGX already. And we have our computation verification protocol. And on top of that, for our oblivious operators, SQL operators, we have, I guess we only have 3 here, but we technically have 4 core operators. So we have filter, aggregation, join, and sort. So those are kind of the core SQL operators that you want to support in SQL analytics system. And finally, on top of that, we have oblivious query planning, which we introduce a new cost model because now that we are implementing different operators, they cost different. They have different costs. We also have some rule-based optimization as well as cost-based optimization. And I'll go into more details later. So let me first start by talking about how we can do computation verification. So verifying that the query was indeed run correctly. So to kind of before that, let's take a look at how our query execution works. So in Opaque, we have the Spark driver and Catalyst, which is the Spark SQL query planner. We locate them both on the client side, so in the trusted environment. And when the client wants to issue a query, the query is first translated into a DAG of encrypted operators. And the encrypted DAG is then given to the scheduler, which is located on the server side in the untrusted region. And the corresponding tasks are run on the Spark workers. So in this case, it's doing a summation of everything. So what each Spark worker is doing is that it's calculating the the local sums, and then you do an aggregate of the sums, calculate the final sum, and give it back to the client. So what could go wrong in this, right? Actually, a lot of things can go wrong because the cloud can alter the distributed computation by dropping data, right? You can modify data, or you can try to skip a task or maybe replay old state. So here I'll give you an example of dropping data. So it's the same query as before. You're loading in the data into the enclaves. And when you're calculating the global sum, what happens is that one of the enclaves actually, or one of the malicious servers actually drops one of the partial sums, and you get an incorrect result of 23 when the correct result should have been 27. So this is clearly an issue, and we deal with this problem by providing something called self-verifying computation. So this is basically an integrity check that has the invariant that if the computation does not abort, then the execution completed so far is correct. So that means that if the query finishes successfully, then we know that the entire query was also correctly executed. So the way we do this is, I think should be pretty intuitive. So this is just continuing with our previous summation example. Here we have the tasks 13 through 15 calculating the partial sum. So we have the final aggregation task, that's task 20, and that calculates the final sum and needs to verify that it gets the correct. So it needs to verify that it gets the correct partial sums from the 3 dependent tasks. So what we do is that we first give all of the enclaves encrypted DAG of the logical task for a particular query. So again, right, our query planner is located on client side, so you're able to calculate in advance what this DAG is supposed to look like. Now, what task 20 is able to do is that it can authenticate that, given this DAG, that the encrypted DAG is unmodified and everything. Then what task 20 will do during the computation is that it will receive partial sums, and it needs to verify that indeed it has received a correct authenticated output. Right, so this one to make sure that the attacker cannot maliciously modify the partial sums and change the value. So finally, what task 20 does is that it verifies the entire thing is consistent, right? According to the DAG, it's supposed to receive authenticated outputs from these 3 prior tasks, and once it shouldn't receive, more or less than these results, and with this we can actually verify sparse equal computation. So does this make sense? Right, you have the encrypted DAG, and then each step, each task checks its outputs from according to the DAG and make sure that everything is consistent. Okay. All right. So with this computation, self-verifying computation protocol, you can see that Opaque already provides strong security guarantees. Right, you have the data encryption, authentication, and computation verification. But of course, even with all of these security features, you can still leak information from access pattern. Okay, so next, I'll present how we deal with that issue. So taking the same example before, where you're doing a select count from medical groups, so this is kind of the same example as the attack that I showed before. So we want to do aggregation on this, right? But in an oblivious way so that you don't leak access patterns. So let's assume that our data, in this case, is divided into 2 partitions. And what we do is we first start with an intra-machine oblivious sort. So the oblivious sort algorithm is a primitive that we're taking from a prior paper, in this case, an old paper from in 1985 that allows you to do sorting obliviously, and actually it has nice distributed properties as well because it's able to do the oblivious sort in a constant number of shuffles, so in our case 5 shuffles. So what this oblivious sort does is that, now the attacker is a little bit confused because it allows you to kind of destroy the relationship between the output records and input records. So you don't know, given the output records, which input record, a particular output record corresponds to. So I won't go into details about how the oblivious sort works, but talk to me if you're interested afterwards, or you can take a look at our paper. So assuming that we have this nice primitive, what happens next is that, okay, so you can see that everything is nicely sorted. We can just do sort-based aggregation on there, right? Pretty easy. Well, actually, there's still something slightly tricky because in this case, right, because we have the inherent skew in the original data set, right, where you have more more patients with diabetes than cancer. What happens here is that the diabetes group is actually split across 2 machines. It was nice that the oblivious sort was able to kind of nicely partition everything into equal size partitions, but now we kind of have a boundary problem here, right? So we need to be able to aggregate this entire thing obliviously and in parallel at the same time. So how we do this is that we first do a parallel scan on each partition and collect some statistics. And these statistics are include something called a partial aggregate, which is the aggregation info that corresponds to the last row of each partition. It's a little bit confusing, but basically, as an example, right? So each partition is supposed to produce one partial aggregate, and in this case, you look at the first partition, right? The disease that corresponds to the last row of the first partition is diabetes. So we have diabetes 1 as the partial aggregate. And if you look at the bottom partition, the last row is diabetes 3, or the last row is diabetes, and you have 3 diabetes records. So what it produces is diabetes 3 as its partial aggregate. So once you produce these aggregates, you can actually collect them all together to a single partition, single machine. And then what you can do is actually you can send the previous partition's partial aggregate to the next one, right? So that, well, I mean, truly what happens is that the first partition produces diabetes 1, and now it passes its partial aggregate to the second partition. With this information, you can actually do the aggregation for the diabetes group correctly, right? Because you have that information from the prior partition. Does that make sense? This is kind of... So, I mean, I think an intuitive way to think about it is that we need a way to kind of exchange information from one partition to the other, but in an oblivious way, right? Because if a group is split across, in this case, 2 partitions, but in reality, it could span across many partitions, we need to kind of pass in that information from one partition to the other, so that, or one partition to the next, so that you can, in the end, aggregate correctly, right? So what we're doing is basically you kind of do a local aggregate first, collect some information about the group that could span across the boundaries, and then pass that information to the later machines, so that the group or the machine rather that has the kind of the last row, right, of a particular group is able to use that partial aggregate information from prior partitions and aggregate correctly. Does that hopefully that makes more sense? But okay, I mean, if you have questions, feel free. Otherwise, we can always chat offline about how this actually works. Okay, so assuming that this works, what happens now is that using these partial aggregates, you pass those partial aggregates from one partition to the other, and now you can produce the final results, right? And actually, what we have to do is that we need to produce one output row for every input row, because otherwise you will actually beat the group sizes, right? Because if you have more groups, or if you have more answers for one partition than the other, then you know that that partition has more groups, right? So what happens is that we'll just simply pad the output with dummies, right? So that you have an equal number of output rows as the number of input rows. And after that, we can simply end the aggregation operation with one final oblivious sort, so that we sort all the dummy rows to the bottom, right? And then you can just simply kind of remove the dummy rows and produce the final result. So I showed that you can run aggregation in this distributed manner using our Oblivious sort primitive. And actually, I mean, because sorting is so broad, it can be applied to join operators as well. So that's very nice. But as you can see, what ends up happening is that you still have 2 different sorts, right? One in the beginning where you're ordering everything, and then one at the end where you're reshuffling to make sure so that you can get rid of the dummies, right? So can we actually do better than this? Can we improve the performance further? And the answer is that yes, we can actually do that by kind of exploiting some, or by approaching the problem from the database query optimization perspective. So here I'll give you an example of our rule-based optimization that actually solves the problem that I mentioned. So let's start with a similar aggregation query, except this time let's add a filter on age. So again, we're doing select count from medical. We want to group by disease, but then here we just have an extra filter on age. This SQL query can be translated into a tree of operators. So in this case, it's pretty simple, right? You have your medical table, it goes through a filter and aggregation. So yeah, so with this, we can already apply well-known SQL rules such as predicate pushdown, but we actually make the following. So, with the view of this, we actually have the following insight that you have this tree of logical SQL operators. What you can actually do is you can actually split each logical operator into smaller opaque operators, and then take a global view across the entire plan and remove some opaque operators to improve performance. So let me show you what that means. So here we have the medical, the same query, right? You have the medical table filter aggregation. And when you look closely, what actually happens is that when you're going through with this, what you do is that you have the medical table, right? You need to do a scan to load that into memory. And then the filter itself is actually, the entire filter operator is actually split into 3 smaller operators. The first is a simple projection that projects the filter column, in this case, the age column, into a new column that contains 0 and 1s. So 0 means that you should keep the row, and 1 means that you should remove the row. After that, you can we do an oblivious sort on the 0, 1 column, so that we kind of sort all the 0 rows before the 1 rows. And finally, we apply an actual filter and remove the 1 row, the row that we don't want, right? So now with that, the filter logical operation is done, and the aggregation, as I went into before, right, it consists of, again, 3 smaller operators. So you have the first oblivious sort, and then kind of the slightly complicated aggregation protocol that I went into, and then final oblivious sort that gets rid of the dummies, right? Okay, it's just animating that. So as it turns out, we can actually look at the opaque operators in more detail. So let's take a look at this box sequence. So we have the first sort, which sorts on the 0, 1 column, right? The projected 0, 1 column. And then we have the first sort of the aggregation operator, which is the second global sort, which sorts on the disease column. And we actually combine these two into just one sort, but it's a multi-column sort. So that what we can do is actually we can do, instead of filter push down, right, in regular database, you can do filter push up. So you push down the sort operator and combine these 2 operators together into one multi-column sort, so that you get rid of one extra sort. Right, so let's take a look at this new sequencing action. So first of all, you start with the scan, right, as before you load the data. You do your same projections before, projection into the 0, 1 column. And then you do a multi-column sort on both of these columns, so on the disease and the 0, 1 column. So that, right, so you sort both of these at the same time, and then you can just go ahead and do this filter as usual. So that you get rid of the rows that you don't want. So what happens is that after the filter, the leftover rows are already pre-sorted on the disease column, which is very nice. And then you can just go ahead and do your regular, the rest of the query. Yeah, so with this, we're able to eliminate one oblivious sort. Right, does this make sense? Questions about how this works? Okay. Yeah, so this is pretty nice because we are able to kind of I mean, because this is rule-based optimization, it can apply to any opaque query, and you could just take a look at it, decompose it into smaller operators, and apply this rule. Okay, so yeah.
One thing is that you haven't eliminated a sort, but you possibly change the amount of data you need to exchange, right? Because the two-column sort, depending on whether the columns could be, depending on where those boundaries are, how the data are partitioned, and where those boundaries are in your network, you may be exchanging more data.
Actually, in that case, we would always win, because in the first sort that you have to do for your filter, right, you actually have to shuffle the entire data set in order to make sure that you're filtering securely, basically. So we have to do a sort on the on the entire data set anyway, and after the filter, we do another sort, right? So what we do is push that smaller sort into the bigger sort, so that you only do the first sort. Does that make sense?
It might. I have to think about it. I mean, I guess the point is that depending on how you optimize it, you may change your communication pattern, not necessarily in a way that it makes it, well, a way that may make it less oblivious, depending on things like timing, but that may also change the amount of data you have to shift back and forth.
I mean, so first off, our oblivious sort, I mean, because it has the oblivious property, it's actually always, the entire access pattern is deterministic, so there is no really, I mean, you can tell that it is sorting, I suppose, but then other than that, you would still have the same access pattern as before. And also timing, that's not part of obliviousness, I guess, so we don't protect against that.
That seems like an important part, right?
Yeah, but I mean, it's not in the definition of obliviousness, but sure, you can always add that into our system as well. But.
Yeah, I guess my point was that when you change your query pipeline by changing things around, the amount of data that you send, say, over the network from one stage of the pipe of computation to another can change. Now, it could be that
I see what you mean.
Space obliviousness that, I mean, I guess for space obliviousness, you're always going to have a constant bandwidth at each stage of the pipeline.
Right.
Yeah, but it might certain.
Yeah. So you mean the sizes, right, of the operators will change? Yeah, actually, so that's not something that we solve in our oblivious mode. Actually, we have three different modes of operation in opaque, but we have actually oblivious pad mode that actually solves exactly that. So it's a little bit, but yes, by looking at the output. So in the base oblivious mode, you can reveal the output sizes of the operators, but then our oblivious pad mode, which is mentioned more in the paper, I mean, you basically do padding so that you don't leave any of that information until the end.
That's not quite what I was saying.
Oh, okay. All right,
but
so
I understand that. That's a good point.
Yeah. Okay. All right. So next, let me show you an example of our cost-based optimization. So with this, we make the observation that actually in a realist database, not all of the tables are sensitive, right? So in this case, we have hospitalized patients, we have another table on disease and medication. And we can see that, the hospitalized patients, obviously, that's very sensitive. But then the other two are kind of well-known information, right? That doesn't need to be sensitive. So our system is able to operate in this mixed sensitivity so that sensitive tables are run with oblivious operators, and then the other tables are not run obliviously. So if you just just do a computation on the disease table, right? We won't run the operator. We won't run the oblivious operator. We'll just run the kind of default encrypted operator. So with this, we can already get rid of some of the overhead, right? If you're not computing on super sensitive data anyway, then you can run it with I guess less secure SQL operator. This mixed sensitive context actually also presents an interesting problem, because we need to make sure that in every plan, right, every operator security level is chosen carefully so that you don't leak the access pattern information about any of the sensitive tables. So if you look at this plan, right, you have first of all table A joined with table B, and another table C joined with table D, and then finally another join, right? And in this case, C is sensitive. So that means that the join between C and D should be made oblivious, right? It's also sensitive. But actually, you need to further propagate this up, right? Because the output of C join D is also sensitive. So this is the actual secure plan that you need to come up with in the end. So what basically happens is this sensitivity propagation property, where you need to propagate obliviousness from leaf to all the way to root. Right, but then note that still on this side is fine because both A and B are not sensitive. So our insight number two is that sensitivity propagation, this property introduces a new dimension for query optimization. So let's take a look at a specific example. So the same table as before, you have patients, disease, and medication. And in this case, we want to find the least costly medication for each patient. And we're making some extra assumptions here that the patient table is rather small. Here's a slightly complicated SQL query here, but I mean, what you need to know is that basically it boils down to a three-way join. So it's an aggregation query followed by a three-way join. Right, so this is what you come up with. If we feed this new, if we feed the SQL optimizer with our new cost, right, as I mentioned before, we have a new cost model for these operators, then what happens is that, right, on the left side, you have patient and disease, patient join with disease, and then join with aggregated result of medication table. And this one, because patient table we assume is rather small, that means that this will actually have a more selective non-oblivious join, which is nice because then their join is also small. But that plan is also not secure, right? Because as mentioned before, you need to actually propagate the sensitivity all the way to the root. So what happens here is that the plan on the left will actually give you two oblivious joins, whereas the plan on the right, if you just take a look at the SQL optimizer with new costs, it's not great because you need to join two large tables in the beginning, right? But then it's nice because the first join is non-oblivious and the second join is oblivious. I mean, you can't avoid that anyway. But the plan on the right is actually better if you take into account the sensitivity propagation property, and it gives you fewer oblivious joins instead of the first one where you reduce the data set, but then you need to do two oblivious joins. So does that make sense? So kind of having this sensitivity propagation, the security, secure operators mixed with non-secure operators, you will get this interesting kind of new dimension to query optimization. Okay, so with that, let's take a look at our evaluation. So for evaluation, we ran some single machine experiments as well as distributed experiments. So on the single machine, we use, our in-house SGX machine with 4 cores, 64 gigabytes of RAM, and the Intel SGX is configured with 128 megabytes of the enclave page cache, which is the the encrypted enclave memory, and actually only 93 megabytes of that can be used for actual computation. And for distributed experiments, we ran this on a cluster of 5 SGX machines. So there are 2 questions that we want to answer with our evaluation. Right. So first of all, how does Opaque compare to the default vanilla insecure Spark SQL? And to answer that question, we ran both systems on this benchmark called Big Data Benchmark. It has 4 queries total. We only run the first 3 queries because the 4th query is kind of out of scope. It's an external script query, so not really relevant. And we ran this on 1 million records. And the second question we want to ask is, how does Opaque compare to a state-of-the-art or state-of-the-art Oblivious systems? And at least, I guess this was a year ago, but a year ago, the state-of-the-art Oblivious system is GraphSC, which was an Oblivious graph analytics system implemented using crypto, actually. So for this one, we compared our system with GraphSC on the PageRank query. Right, so here I'll show you the big data benchmark compared with the vanilla Spark SQL. So we actually benchmarked 2 different modes of operation for Opaque. So the first one is when we have data encryption, authentication, and our computation verification protocol in there. right? So no obliviousness yet. So here you can see that the darker gray bar is Spark SQL, and then the lighter gray one is Opaque. And here we actually get overhead of minus 0.47x to 2.3x overhead, because we actually implemented our thing in C++. So yeah, so it's a little bit faster than Scala. Right. Of course, if you look at obliviousness, then we have more overhead. In this case, 21x to 45x overhead, compared with the baseline Spark SQL. But we think that this should still be usable on smaller data sets, for really sensitive data sets that you want to predict. With larger data sets, I think there's some more work to be done. But if you can also tolerate, these are for batch analytics workloads, right? Not online workloads that need to be very latency sensitive. So it might also be possible. Okay, so compared with GraphSC, we ran this on a single machine. So the x-axis shows the kind of the rough estimate of the graph size, and y-axis shows the performance, and we can see that Opaque actually has a 2300x performance improvement over GraphSC. And to be fair, this is because GraphSC uses garbled circuits with pretty heavy crypto primitive instead of enclaves, so that's why we kind of have a huge speed up. And actually, we tried to run GraphSC with a larger enclose, but then it just crashed. So that was a little bit unfortunate, but okay. Right, so in conclusion, Opaque is an Oblivious and encrypted distributed analytics platform. We actually have open source our code at github.com/ucbrise/opaque. We actually have some collaboration with IBM, so they're using it for 2 use cases, which is pretty exciting. And I'll quote them saying that Opaque is surprisingly stable. So, if you want to use it, you might, it's probably better than some of the other, secure systems out there, or secure research systems out there. In terms of the future work, so one of the things that we're looking into, both for Opaque and the RISE lab in general, is the federated setting. So in this setting, it's kind of interesting setting because, here we built Opaque for the cloud-based setting, right, where you're kind of outsourcing the computation to the cloud. And, there are existing systems based on that already, and we can add SGX to it and be secure. But this is a setting that's very interesting because for once, security and actually allow you to, or encourage people to collaborate more, right? So for example, one of the use cases that we found was multiple hospitals that might be possibly competing with each other. They want to jointly compute a model that predicts flu outbreaks across the state of California. So that's very interesting because, for obvious reasons, the hospitals cannot release their data to other hospitals, right? But at the same time, if you build a model across all of the user's data, all of the patient's data, then you could possibly get a much higher quality model than if you just computed that model from one hospital's data, right? So this is a case where, if you didn't have a secure way of doing it, people wouldn't even think of collaborating because that's just not going to work. But then with our technical contributions from the security side, you can either do this with SGX, or as what I'm looking into now, actually doing this using pure crypto. I think it's very exciting to kind of look at this federated setting. Okay, and with that, I'll conclude, and thank you very much, and please let me know if you have questions.
Where is the overhead come from? Is it because the memory size is 1.8 megabytes, or because they had a lot of interactive between different machines?
Do you mean the Oblivious mode or the encryption mode? Because if you look at just purely encryption mode, right, we're not doing any of the fancy Oblivious sorting.
Yeah.
It's actually quite competitive with the underlying minimalist Spark, right?
Yeah.
If you're talking about obliviousness, that really comes from the fact that we are doing more heavyweight. We're doing extra extra computation, right? Is before, in order to hide access patterns, you need to make some extra dummy accesses in order to hide that. So just because of that compute overhead, it's you kind of see the 21x to 45x. But I do agree that if you do have a bigger EPC size, you will also kind of improve the performance. But either way, let's assume that you have a very large EPC size, right? And let's assume that EPC itself is already oblivious. Then you still need to add extra computation on the network level, right, in order to hide the network access patterns. So yeah, I mean, that's kind of where the overhead is coming from.
And also communication, right? I mean, maybe describe that.
It's
also communication, right? Which is that, you mentioned that, well, you need, even if you don't need to send the data, you'll pad it with extra dummy data and send it just so that people won't be able to check how many packets you're sending.
Or
how many records you're sending.
Yeah, just the size of the network messages exchange, right? That can reveal information.
Yeah, the size and quantity.
And
lots of other things. I mean, in network, analytics like intrusion detection, for example, often you look at timing patterns of packets is very important for describing their content. They're all encrypted. You have no idea what they are, but by looking at the timing, it's very important as well as the actual length of the data. But just from timing, length, and request response patterns, you can actually infer a huge amount of information. So from the communication side, it seems to make things oblivious, you're going to have a lot of overhead as well as computation.
Right. But I think I just want to emphasize again, right? For our paper, we were looking at the access pattern, pure access pattern. We didn't really take into timing. We didn't take that into account. But you can certainly apply prior techniques. But that will add more overhead, I guess.
If you look at recent side channel attacks, they've often focused. Well, recently, Spectrum Meltdown, they're all timing based, right? So it seems that timing obliviousness is a very important quality if you want to avoid information leakage. Do you have thoughts about how to extend this? You sort of have space obliviousness, I guess you might say.
Yes.
But clearly, timing channels and also things like power channels, et cetera. But there are all sorts of resource conflicts that can reveal all sorts of information. But the timing is a huge one, and all the recent ones are sort of based on that. Do you have thoughts on how to add timing of obliviousness?
Yeah. I mean, it's kind of similar, right? So instead of padding in the space dimension, you kind of pad in the time dimension, right? I mean, that's kind of the only way that you can do it. So you can certainly, again, apply that techniques, just add to our system, right? Add that on top of our oblivious system already. But it will increase this overhead further. I don't know how much it will increase it by, but I agree it is an important problem. At the same time, I think, from my experience with industry at least, I feel like the bar is kind of low, right? In terms of what people actually do in industry, that even to get that first step, right, to get this part working, the data encryption, authentication, computation, verification working, that's already a huge plus over what people already have today. So, I mean, I agree that would become, that's definitely very relevant, but I think as a first step, into adopting the system, I think the first one is probably, it would be nice to get people to work, adopt the first mode, and then we have the obliviousness and side channel and the cache timing, or I guess general timing side channels in there as well.
Yeah. Often in cloud environments, you have sort of ephemeral VMs or containers, but often some sort of persistent store like a block store, for example, for your database. And it seems that the access patterns of that block store are very important as well. Does this approach of sort of space obliviousness mean that if you monitor the access patterns either to the block store or to the disk or flash or whatever, does it apply to that as well, or is it just at sort of a higher level of basically steps in the database query pipeline?
Yeah, no, actually for Spark it's a little bit different because the underlying system, right, is memory based. So what happens really is that you kind of read the entire database into memory, and then you operate in memory RDBs, right? So, but yeah, so that's a little bit specific to the implementation. But our design can certainly work if you have a system that uses on disk.
You know, like a lot of, for example, a lot of storage systems use caches, and they only like write back the records that have changed. And so, for example, if you look at the number of those write backs, you could say, oh, well, you know, that might tell you some really important information about like what records, you know, the number of records that have changed. Unless you know, on the other hand, you say, oh, well, you know, if you don't do that, well, then you add a bunch of extra kind of bogus writes. Well, now all of a sudden your flash, you know, or degrades at a much higher rate. So it seems like there are definitely some challenges in that area.
Yeah. I mean, yeah. No, I definitely agree. I think it would be very interesting to look into that. But again, you know, for our system, everything is in memory. Yeah, so you can just, you know, do things like that. Okay, other questions?
If I mean, for this test had a 1 million record, right?
Mm-hmm.
If you have more than 1 million, for instance, 10 million, what will happen for the performance? I mean, in that case, I mean, you need to read the data into the EPC and for decryption and encryption, and will it affect the performance?
Yeah. That's a great question. So I guess in terms of scalability, right? So our so in terms of our Oblivious operators, the like by far the largest amount of overhead come from the Oblivious sort algorithm that we use. And there are two parts to that. So first of all, the local sort, which also need to be made oblivious, right, with respect to memory, and the kind of network part of the sorting algorithm. So the local sort, yes, we're using a sorting network right now that is kind of dependent on the size of the Oblivious memory that you have. So in this case, you can maybe assume that as the size of the EPC. So the overhead is n log squared n, where it's n, you can kind of think that it's the number of blocks that you have. So maybe you know, you can load 2 blocks into the EPC at the same time and then merge that. And right, so if you have like n blocks, then I mean that's the kind of the amount of overhead that you have. And in terms of the network portion of our Oblivious sort, that one's actually pretty nice because we always have a constant number of shuffles, so that scales pretty nice with the data size. So you don't get like any log and or like n number of shuffles or anything. Yeah. But yes, but definitely the single machine. It would be nice to have a larger EPC size. Yeah. Go ahead.
For your evaluation setup on the Spark side, how many slaves instances per server?
Yeah. So again, that kind of goes back to the size of the EPC because it's so small. We actually found that it's better to have one worker per, like one thread running per machine. But yeah, so we get our scalability from the Oblivious sorting algorithm. So because that one's distributed, yeah.
And also initializing enclave has a initial time.
Mm-hmm.
Is that considered into this?
I don't think that was considered into this, but then that's not such a big issue because you can consider these to be long-running workers that you initialize a worker, you initialize the enclave in the beginning, and you can run multiple queries. Yeah.
So they don't go away; they're persistent.
I mean, I'm not sure you can say it's persistent, but you can, like, as long as it's running, you can keep the enclave running. You don't have to. It's a one-time cost in the beginning. You don't have to keep on re-attesting and loading things.
We're out of time, so thank you very much.
All right, thank you.